Okay, so we ended with descriptive stats, and I have the script from last time open. So we covered how to calculate the mean, the median, and the mode, which are all measures of central tendency. And then we sort of ended with when would I use each one, so why do we have 3 of them? And that's because there are different purposes for each one. But the mean is not necessarily, if we just talk about ratio data, because that's mostly what we're going to do this semester, always the end answer. So if I tell you that the mean for the class is on the first test is an 81, you'd be like, okay, and okay, so what's a B? But how many people scored above and below that? So what we're going to do today is add to our available types of statistics, talk about variability. And this is what you'll see in research papers. You'll see usually the mean, median, and the mode, mostly the mean, and then something else as a measure of how much the spread around the data is. Okay. So we talked about, let's say we have a normal distribution, normal-ish. Start with the mean. Okay. Variability is how much or how wide the distribution is spread. So we could talk about it as a range. So the range is literally one of the lowest score to the highest score. That one's pretty easy. And that I don't know that people report terribly much. They might when they're talking about scales that have specific criteria. So for example, the CESD, which is a depression scale, has kind of cutoff-ies type scores, like people above this are considered X. So often people give them those kinds of ranges. But when I'm reporting my research, I don't talk about the range just a whole lot. Okay. Except to maybe say that this scale could range from 4 to 28. But the range is the lowest to the highest score. And so to calculate the range, what we would do is find the lowest score, find the highest score, subtract. So I guess we're just like getting our feet wet slowly because most of these concepts shouldn't be too hard. I'm trying to get really into using R. So if the highest score, I think yesterday was, or Monday was 24, I think the lowest was 10, that would be about 14 points. But that's why the summary function is so great. Somebody yesterday, I think you asked me, why would you ever not use the summary function? There's only a couple times. It will give you min and max. Or, if you didn't want to ever do math, because I know people have a fear of math, you could make R do it for you. So what I'm going to do is I have that data set. This script is online if you don't have yours from last time. I'm going to have to rerun my column here because it doesn't exist because this is a new R. If you're opening your computer, it might still be there, but on mine it's not. So I'm going to rerun this. So I've got our data from last class. Now I could just do the summary function. I have my min and my max. I can't believe I remembered that. I'm such a squirrel. That's amazing. So I could just do 10 minus 24. It's just pretty easy math, 14. But I'm very pro not doing math because while I'm good at it, I am also distractible. So in the middle, I get forget what I'm doing. So I could do max of my column and min of my column. And a tip, if the little window thing with the stuff for you to type doesn't show up, that is like the most undescriptive thing. So if I start typing, it's supposed to give you that. If it's not showing up fast enough for you, hit tab. And it'll show up a little faster. Okay. Alright, so I could do max of my column. Remember that na.rm is that remove NAs, or it will just spit out NA at you. Okay. Minus the min. And that'll give it to me directly. Oh, or it'll freak out. It doesn't like that minus symbol, it looks like. There we go. Sometimes cutting and pasting doesn't always work. So it told me 14. That would be really useful if you just don't want to think. In the summary function, you've got the min and max. Yeah, or good example, if there's a lot of decimals, and you have to carry a number. Okay. If it's small numbers, it's probably just as easy to use the summary function. All right, so that's the range. So we've got range. We're going to talk about variance now. There is no symbol for the range. You just say range. Variance with a C. There you go. The symbol for variance is either SD squared or S squared, depending on which book thing you're looking at. This is a little bit harder of a concept to explain. So what variance is if I have the mean, it's the average squared deviations from the mean. That is like not a helpful definition probably, right? But it's the idea of like how much on average are people varying from the middle. So if we, example I always like to use football because I like football. If we have the players on the field and they're in the middle, how much on average are far away are people from them? So if you're at our stadium, it's not very far. If you're at a stadium like Michigan, like one of the largest stadiums, you might be kind of far away, right? Because if you have 2 or 3 tiers, I know Kyle Field has 3, and if you're way at the top, they might as well be ants down there. So how far away on average are people from the middle? And so what happens is we calculate each individual person. Right? Remember, these are all still people. I'm going to use X for person here.
You're still a person.
Yes. They're all still people. Next week they won't be people anymore, but we'll talk about that. And so we measure how far away everyone is from the middle and take the average of that. So we're measuring how far away they are from the middle and averaging it. Why would we square that? So very simple, if I can do this correctly today, very simple example where we have, let's go really easy, 10, 15, 20, 25. So let's say people scored a 10, a 15, a 20, and a 25, because I like nice even numbers. So I could get the mean of the example here, right? So 17 and a half. So if you look at the formula, if we have to figure out how far away they are from the mean, the first step is to subtract. And so that's what this little formula has here. So x minus the mean. It doesn't have x bar because I have to change it. Okay, so x minus m. Or x bar if you like just numerical symbols. Right, so that's negative 7.5. Oh, you guys are going to have to help me. Negative 2.5. 2.5. Should be 7.5. Yeah. Yes. Right, so that's the distance from the mean. If I just totaled those, what does that add up to? 0. Yes. Yay. So I can't just total the distance from the mean. That would be like nice and easy and simple, but unfortunately, because the mean is the middle, the total distance from the mean would be 0. Sometimes people suggest using the absolute value, but what we've settled on is to square them. So that's why it's x minus m squared. So variance is the average squared deviations. Okay, so if I take away the m here, if I could, left d here, that's just this formula for the mean. Right? X over n, the sum of x over n is the mean. And so all we're doing is adding, or really subtracting the mean. So subtract the mean from everybody, divide by n, that gives you an average distance from the mean, but it's squared. Okay. So I told you the square distance from the mean on your stats test was 100 points. You'd be like, what? Because you can't get 181 points or negative 20 points. You can't get negative points. which is good. Right? So a lot of people don't use variance because it has this issue of being squared. So instead we're going to use standard deviation. I'm not ignoring my note down here. I'm going to come back to it. Okay, so we got variance. The sum of each person minus the mean squared divided by n. But the issues of variance is that it's tied to the scale it's in. So large scales, the 100-point scales, get very big variance very fast. Small scales have small variance, and it's squared. So that makes it hard to interpret. Instead, what we're going to do is take the standard deviation. Standard deviation, which is just the square root of that. So we had to square it to deal with the can't add up to 0 problem. So we're just going to unsquare it. It's a pretty simple solution. And what that does is it standardizes it. So standardization is going to be a big theme in this class. The whole next test is going to be about standardization. So putting things all on the same scale so we can compare them to each other. So we're not comparing apples to oranges. So it's standardized. It brings the numbers back into the original scaling. So if I told you it was a 10-point spread around 81, that makes more sense. People were scoring, on average, a 71 to a 91. I don't really remember what it is, but a 10-point standard deviation makes sense. 100-point variance, not so much. It is still biased by scale. So if you have a 1 to 5 scale, you cannot have 10 points of standard deviation, because there are not literally 10 points to move. So scales that are small, meaning the range of the scores is small, will have small standard deviations naturally. Scales that are large can have large standard deviations. So getting used to like what's a big standard deviation and what's a small standard deviation takes some time sort of thinking about how big is the scale. So for example, if I have that 1 to 5 scale and I tell you it's the standard deviation is 1 point, that's pretty normal. Because 1 point makes sense around the top and the bottom. If I tell you it's 2 points, it'd be really weird. Because that's 2/5 of the scale. I tell you standard deviation for a 100-point scale is 1 point. That would be really small. It's 1/100th of that scale. Does that kind of make sense to people? Yeah. But if I tell you it's 10 points, it's not so unusual. If 50 points would be a lot. So you kind of have to get used to thinking about standard deviation based on the scale. And then for the next test, we'll talk about how to solve that issue, where you don't have to think about anything. You just look at the number. All right.
When would we use the other one?
Variance?
Like, I can understand why we would use standard deviation. When would we use variance over standard?
Variance is just sort of like a way to get to standard deviation since it's part of the formula. When we get to talking about ANOVAs, we'll come back to variance. But that's like third test towards the end. Oh, I'm so glad you said that though. So sometimes what people will do is this piece, it's the same, these two things, is often called sum of squares, or SS, which always makes me laugh. I spent part of the summer in Germany, and so I'm always like, sum of squares, no, I'm actually in Germany. They literally mean SS this time. Right. So sum of squares is the sum of the squared deviations around the mean. So if you see a question about sum of squares, they're talking about the numerator on both halves. And then when we get to ANOVA, to answer your question, we're going to use sum of squares a lot. So, because ANOVA stands for analysis of variance. So we go back to variance for reasons that we'll get to when we get there. Okay. Without being confusing today. All right. So the issue about this formula, I think I'm trying to back up a little bit, is this number, this letter. So the book at the moment is talking about calculating the variance and the standard deviation for a population. So they use n on the bottom. Okay. However, most, I went to this slide, sorry, I'm jumping around. Most people use n minus 1 as the denominator. So we're going to talk about biased estimators and unbiased estimators. And that's the way that I describe them in the homework and the notes and the test. Okay. So not to skip the slide, the standard deviation is the typical amount the scores vary or deviate. So when you're trying to distinguish on a quiz or the homework if it's variance or standard deviation, because the wording is tricky, if it says squared anywhere in it, they're talking about variance. If it doesn't say squared, they're talking about standard deviation. So that's the point of this slide. Okay, try to get my hand waving out today. Okay, so if we're calculating this in R and we use these two functions, you'll see they're very similar to the mean. Right, so it's var, column name, and SD, column name. These are not part of the summary function, which always makes me sad. Okay, because standard deviation is one of those popular things I'm always calculating. That will give you the unbiased estimator. So unbiased estimators are for samples, and the denominator is n minus 1. This is jumping ahead a little bit. We'll talk about this more on exam 3. Well, what do I mean by unbiased? So we're taking lots of samples from a population and calculating the average distance from the mean. We want to kind of not overestimate that. So if you have a small sample and you have an outlier, that's going to make it really big, right? If you have a small sample that's very homogeneous, it's going to make it really small. And so we've got to deal with the issue of like, sample isn't a population, right? It's a group of people within that population, and we can't get it perfectly right. So until we talk about degrees of freedom, which again will be a couple tests from now, the way I always think about unbiased estimators is that it takes away one of your sample people as just like maybe you screwed something up. Okay. So it overestimates the variance, which you would think would be bad. But in statistics, a slight overestimate is better for you. And the reasons for that are lots of concepts that we haven't gotten to. So I just take my word for it right now. And we'll talk more about especially why would you want to slightly overestimate in the next sections, because I don't want to like too much at once. The biased estimator is for populations, and it's just going to be n. And I always think of it as being biased, and that's on this next slide, because it's kind of a biased thing to say that you know everybody's answer. So if you truly have the entire population, like if I decided the population was just this class, no other statistics test, no other students, then I suppose I could go with n. But that would be silly, right? There are lots of other students, lots of other stats classes. So I should try to unbias my answer. Which I guess is sort of a relevant topic this week with all the protests going on, biased and unbiased answers. So I think it's problematic to think that you know everybody's score. Right? So we're going to unbias the scores. Unfortunately, the book stuff is all asking you to calculate biased. Okay? Unless it's an essay question that I've edited and specifically says biased and unbiased, they want this one. Okay? The problem is that R gives you the unbiased one, because I don't know anybody in research that uses the biased statistic. Because to say that you use the biased statistic causes, just think about that for a second. I use the biased one. Right? So we're going to do both. So let's start with unbiased. I don't know why I copied that. I could type it. Okay. So first one for variance is VAR. Your column name, which I called my column, NA.RM, and true. So the variance of our column is 14 points. Let me go back and run the summary just so I can look at it. Okay. The mean we decided was 16 points. So the average square distance around the mean is 14 points. Okay, so that means people on average squared 2 points squared to, I can't math, 30 points squared. Oh, that's a headache, right? So instead, let's calculate the standard deviation. So SD, my column, NA.RM equals true. 4 points makes more sense. So the range of the data is 10 to 24. So our histogram runs from 10 to 24. Our mean was 16.22. On average, people varied about 4 points. So that's up to 20-ish to 12-ish. I don't want to math. So most of the data is between 12 and 20. Not everyone, but most of the data. Yeah.
So would those be our quartiles then? Like, is that so 50% of the data falls between 12 and 20?
Not 50.
Okay.
That's going to be 64%.
Okay.
We'll get to z-scores. We'll talk about how that works.
Okay.
The quartiles is 15 and
that's
18.
right.
Right. We haven't quite got to that. It's in the end of the notes, but very bottom 25%, 50%. 75% very top.
Okay.
So this actually breaks it into floors for you. But
But
most
would-
people like standard deviation a little better because that covers usually the biggest hump part.
Okay. So, but what we know now, we don't know how to determine how much of the data appears in between that.
Right, not yet.
Okay.
That's why when people talk about IQ, and I say most people are between 15 points above and 15 points below, they're talking about standard deviation. And that's 64% of the data, not 50%.
Okay.
Which is a easy misinterpretation. It would be beautiful if it was quartile, but it is not. Because normal distributions are not square. Okay. So that's how you can calculate the unbiased ones. Let's do the slightly harder version, which is biased. And I found this beautiful thing on the internets. What this will do is set you up a function. Okay, so this is something new. So I'm going to copy this verbatim. I don't want to type it. And what it does is it calculates, it uses variance here. There's my variance. And it calculates the variance and then sort of corrects for the n-1 problem. Now, I don't think we've done anything yet where we set up our own functions. We sort of did a little temporary thing up here to talk about modes. But what you do when you run these two, you'll see what happens is they pop up over here under functions. So we just made our own functions. Because R doesn't really come with an unbiased estimator function. We made up our own. And by we, I mean somebody on Stack Overflow. God bless the internet. Because I went searching. How do I unbias this? And somebody was like, you can write your own function. Here. I'm like, perfect. And now what we do is pop.var. So after I run those two lines, sorry, let me back up. It'll pop up as an option. It's pop.var. Put in my column. I'm not going to do na.rm because that's not part of our function that we've set up. And the population variance is 13, so it's slightly lower. What will always happen, because math, is that the biased estimator will be smaller and the unbiased estimator will be larger. So you can tell if you're doing it right. Because if you divide by a bigger number, that makes the overall thing smaller. So So in our example here, our variance, our unbiased estimator is 14.5 points. Our biased estimator is 13.7, so slightly smaller. And then we do the same thing. Oops, stop. So pop dot SD in my column. So those 3.71 versus 3.81. So once you bring them back to the scale of the data, often the difference isn't large. If you have a very big sample size, the difference is pretty tiny. If you have a really small sample size, like 5 to 10 people, the difference gets really kind of big. Because if you think about it, if I have larger samples, I'm probably better at knowing what the population is going to be. So that one number that I might be wrong about isn't a huge difference. Okay, so that's probably the trickiest part of this chapter is that unbiased versus biased thing. If it's a multiple choice question, they're asking for biased. On essay questions, I ask for both. All right. So, this is just kind of summarizing what I said. You will have to run that every time you open R. So the functions don't stay unless you never, like for some reason, R never like closes any of the stuff in the environment window. And so my thought is maybe start yourself a file that's just things I should run before I start. That includes your libraries, that theme coding for ggplot, right, that you have to run every single time, and these special functions. You definitely should have something for yourself that maybe is something like this, that has the little comments on what everything is. Okay, you can use mine, that's fine. But especially keeping comments for yourself, like be sure you run this every time. Otherwise, you'll try to do this, and it won't work, and you won't remember why. Our lab has a file called useful functions that I will go and open every once in a while when I can't remember how to do something. Especially if it's something we only do like every once in a while. Like this would be something you would only do every once in a while. All right, last thing. I think it's interquartile range, and then we're done. So to get back to Caleb's question, we've got the min and the max, the average distance around the mean, which says 64% of the data. Sometimes listed as S. So we're also going to do IQR, or interquartile range. And that's 50% of the data. So where's the range of people that scored in the middle 50 is what interquartile range gives you. So that's going to be like here-ish. So we're breaking the distribution into 4s. Okay, instead of z-scores, which is what standard deviation is for. So IQR measures the distance between first and third quartiles. First quartile is 25%. The median is 50th mean. Third quartile, 75th percentile. So it just takes 75th minus first, or I said that wrong. Third minus first, or 75 minus 25. So you could look at the summary function and just subtract. But I'm pro not subtracting. So the function for it is IQR. See, this will be a common theme this semester. Like, don't do math. Make R do math for you. It is a math program. So I'm going to rerun my summary to show you. So between 15 and 18 is the interquartile range. So 3 points. That's not very hard math. But back to your comment on decimals. I'm going to add that to my notes next year. So IQR in caps. This is one of the only things that's in caps. Mostly are lowercase. There's only a couple of little annoying times that it's not. So my column, and then our na.rm thing. And it tells me that 15 minus 18, or reverse, is 3. That's one way you could check yourself too, is run the summary and make sure it looks right. Okay. So that covers mean, median, mode, and then some examples of how to describe the distance around those. So I could start with the range of the data. I could come in some and talk about the standard deviation around the mean, or I could come in even more and talk about the interquartile range, which is more for the median. So most people present standard deviations with mean and interquartile ranges with the median. So that makes a little more sense. Since the median is the 50th. It's like right in the middle. All right. So let's pause.